resistivity increases, and as temperature decreases, resistivity decreases. This property, though not applicable to the conductors, but in case of other materials, it is found as temperature decreased, the resistivity decreases, and for many of the materials, at a particular temperature, lower temperature, their resistivity falls to zero and conductivity becomes infinite. This property is known as superconductivity. This can be represented graphically in this way. The resistivity rho drawn against the temperature. Then it is found that this resistivity drops in this way slowly, and at a particular temperature it becomes directly zero. This temperature is therefore known as critical temperature. Therefore, below critical temperature, these materials are become superconducting materials or superconductors. Mercury, having the property to drop its resistance zero below the critical temperature, that is boiling point of helium. It is specific property of mercury below which it becomes superconductor. Many of the insulators are there below certain critical temperature, they showing superconductivity. But aluminium, gold, copper, silver, though these are good conductors, they are not showing superconductivity property. These superconductors having typical properties, these properties we are going to study, and one of these property is zero resistance. As they are superconductor, they should have zero resistance. This zero resistance can be studied in this way. The sample of superconductor is in this way, connected to the battery. It is connected to the battery in this way along with P, and at the same time it is connected across the voltmeter V. It is observed under normal situation. Whenever we apply the battery and key, we are finding the electric current flow through this at normal temperature. Then voltmeter shows certain reading. This reading means potential drop is existing across it, means sample having certain resistance. But when we drop its temperature below its critical temperature, the voltmeter suddenly drops to zero reading. It shows no deflection. This means no potential difference is developed, and according to Ohm's law, V equal to IR. What this shows? V is 0, I is flowing, and it is dependent on, say, R is equal to 0. In this way, the zero resistance can be studied. For these substances, superconducting substances, it is again the property. Suppose this is a ring of superconducting material. This ring of superconducting material is suppose kept in this way magnetic field. And whenever this magnetic field is suddenly removed, it is found for this ring, the electric current is flowing through the ring. This electric current flowing through the ring, whenever the magnetic field is removed. This magnetic field removed due to the electromagnetic induction, it is showing that current is flowing. This current is developed due to removal of magnetic field. This current, how to flow through the superconducting material for the longer period. Such a type of current which continues for longer period without any external energy supply. This current is known as specific, that is persistent current. This is the property of superconducting materials. It is a persistent current. Many such properties are there for the superconducting materials, and one of those, it is a critical magnetic field. Whenever superconducting material carrying current, that current can be observed steadily with under certain conditions. Whenever we apply magnetic field to this superconducting material, and at a particular maximum value of this applied magnetic field, it is found the superconducting properties are dropped. The superconducting properties are dropped at a particular maximum value of applied magnetic field, that is known as critical magnetic field. And this critical magnetic field, it is represented as Hc is equal to H inside bracket 1 minus say T divided by Tc bracket square. This is what the representation. This represents the critical magnetic field, and variation of this critical magnetic field according to the temperature can be represented in this way. The critical magnetic field varying in this way, this curve represents, this is say Hc, this is say Tc. The magnetic field applied represented in this way and temperature in this way. This representation at T is equal to Tc, critical temperature, the critical magnetic field becomes 0. This is what the representation by the graph. In a particular situation, when we consider about superconducting balls, for superconducting balls, those are represented in this way. The superconducting balls are having magnetic field by their own. This magnetic field existing in this way in case of superconducting materials, then the temperature is say normal. Whenever this temperature is decreased below critical temperature, it is found for these superconducting materials. These superconducting materials, whenever the temperature is less than critical temperature, it is found this magnetic field is ejected and it is represented in this way. This effect is the specific property of superconducting materials, and that is known as Meissner effect. This Meissner effect for these materials is the specific and it is reversible. Suppose this temperature is increased above critical temperature, then the material gains its original property, and therefore this is the specific reversible property of superconducting materials, that is known as Meissner effect. This can be simply represented in case of magnetic field. This magnetic field at any instant, this B is equal to mu 0 into bracket H plus M. And this H is the external applied magnetic field and M is magnetization. When we consider this T less than Tc, less than critical temperature, what we are finding, the magnetic field is ejected, means the magnetic field is equal to 0. From this we are getting this mu 0 into bracket H plus M equal to 0, this H plus M equal to 0, and from this we are getting this M divided by H is equal to minus 1. But this is the magnetic susceptibility type that determines the behavior of the material, and whenever the magnetic susceptibility is less than 0, it is negative, it is a diamagnetic material. These materials are said to be diamagnetic. These are superconducting materials. Their behavior is a diamagnetic. From this it is clear. The Meissner effect explains the diamagnetic nature of the superconducting materials. Rather than this, we are finding the superconducting materials can be used in a different way, and one way, that is, the two superconducting materials are separated by insulating material in this way. Whenever these are separated by insulating material, then it is found the junction is formed between two superconducting materials, and this junction is invented by scientist Josephson. Therefore it is known as Josephson junction. Whenever junction is formed, it is found the Cooper pairs from one superconducting material transfer, or they link from one section to the other section. Cooper pair on this superconducting material get shifted towards this. Cooper pairs from this superconductor get linked to this. This causes slight flow of current, and this is specific effect that is known as Josephson effect. This Josephson effect is the specific property. Whenever we find in this way the shifting of Cooper pairs, there is a formation of a DC potential, and this is therefore known as a DC Josephson effect. Whenever we apply external magnetic field to this, then it is found the AC current is formed. This AC current formed this situation is known as AC Josephson effect. The frequency of AC Josephson effect, it is nu, is equal to 2EH divided by V. That is what the DC potential applied. In this way, the frequency of AC current developed in case of superconducting material according to the Josephson effect can be determined. The superconductors are of two types. One, it is say type first superconductor. Second, it is say type second superconductors. In day-to-day everyday life there are so many applications of superconducting materials, and for these applications the continuous inventions are going on, and dependent on their property the superconductors are of two types. The type first superconductor, it is specification. Whenever we find the graph of these superconductors according to their magnetization, it is found the rise of magnetization up to certain level and it is falling in this way. The maximum magnetic field in this way so obtained, it is known as critical magnetic field. Means one stage of critical magnetic field that is existing in this way. Below this critical magnetic field, they are having superconducting property, and beyond this critical magnetic field, those are showing normal property. In case of type of superconductor, those having only one critical magnetic field, and below critical magnetic field, those are showing superconducting property. Above critical magnetic field, those are showing the normal behavior. On the other hand, whenever we consider above type second superconductors, then it is observed there is a rise of magnetization up to certain level. Then the fall of magnetization, it is varying too much, and there exist the two situations of variation of property of these superconducting materials, and these two stages are known as, say, HC1 critical magnetic field first and HC2 critical magnetic field second. From this it is clear, between these, say, below critical magnetic field first, those are having superconducting property, and beyond this, say, HC2, they are in normal behavior. They are in normal behavior. Between these superconducting critical magnetic field HC1 and HC2, there exists a stage where they have superconducting as well as normal behavior, and therefore this state is known as mixed or void state. This is known as mixed or void state. On the other hand, if you are going to consider type first and type second superconductors, how those are different. The second case that we are considering, the critical magnetic field is single. Here there are two critical magnetic fields. The behavior in this way, below critical magnetic field, they are superconducting. Here in this way, these materials are obtained from pure elements. These are obtained from pure elements, and these are obtained from, say, heavy elements and their alloys along with the transition elements. These are obtained from pure elements, therefore these are also known as superconductors. These are obtained from alloys, therefore these are known as hard superconductors. Dependent on this behavior, these are two types of superconductors. Rather than this, the superconductors are also of two types, dependent on critical temperature. Say, high critical temperature and low critical temperature superconductors. High critical temperature superconductors, low temperature superconductors. Now, these superconductors are of specifically niobium. Niobium is basic element in case of low temperature superconductors. In addition to these, the aluminium, copper, nickel, these elements are added in a particular proportion. These are having low level applications or small scale applications. In case of these, the specific transition elements are used. In case of these, the specific transition elements are used, and these are having large scale applications. These are having large scale applications. The specification of these are dependent on manufacturing system and the materials added in the basic elements. In case of niobium here, and in case of transition elements here, the specification dependent on the contribution of other elements. The different types of superconductors are typically used in different fields, and one of their field is the specific, say, medical field. In medical field, these are are used in a drug delivery system in day-to-day life.